And it is going from 4 meters. What is the maximum compression of the spring? Now this is probably a test question.
Yeah. I know.
Yeah. Like, because I remember this on the test.
Yeah, he right away told us there's going to be a question like that.
Oh, okay. So you have that. No friction. That's good. So it's 10 times 9.8.
Mm-hmm. Yeah.
Now you want to know how fast it's going down the hill.
Okay.
So you're going to go back to a couple chapters back where we did these and solve for your acceleration down the hill.
Oh man, I totally forgot how to do that.
Well, let's see. You rotate your box so that your normal's pointing up, then your gravity's pointing down. Some of the forces in the x, or some of the forces in the x.
Okay, it's a force diagram.
Yeah, so you have your mass times gravity times sine of theta is equal to mass times acceleration.
For the y-axis, right?
For the x.
Oh, this is for the x. That's right.
So that tells you how fast he's accelerating. And it tells you that this is 4 meters. So you can find how fast he's going to hit right here.
How?
So you find your acceleration, you have your distance, v naught is 0. Kinematic equations.
Okay, so that's how we find that part.
Mm-hmm. But then you find your so from that, you will have this. Like looking at the impact. This is before, and this is on your slope, and this is after. So it says that this was 4 meter, or yeah. And it wants to know how much it compressed, right?
So for that, you would use F equals to negative K delta S?
So then we'll use kinematic, we'll use our we'll use energy equations.
Well, we have spring constant.
Oh, perfect. So we can go,
we can just find the force that it is going down the x-axis, right? Because you're using force diagram already? Or no?
maybe, actually, well, because you're given velocity.
Because it's going to be different forces, right? This is going to be spring force.
Yeah. So what you can do, so what you do is, you'd use this thing.
45 minutes or something.
Yeah.
So you'd use this.
They only give you the answer.
At the beginning, you have a velocity.
Mm-hmm.
At the beginning, you have a potential. At the beginning, you do not have a spring constant. At the end, you do not have velocity, you do not have potential, you do not have spring.
Why?
Because let's say you make your 0 marker right there.
Okay.
And your 0 marker, that's the 0 marker.
Do you still have spring constant?
Oh, we do. We have spring constant.
Okay.
Yeah, so
Okay,
all
that's right.
of it gets transferred into there. So our equation looks like this. 1/2 mv squared plus mgh is equal to 1/2 kx squared. This h, you have to be really tricky about it.
Oh, yeah. Okay. H. Yeah. No,
Because that's this length right there.
Mm-hmm.
So you have to take into account the spring compressing.
Yeah. Oh, that's ugly.
Yeah.
So how do we do that?
So obviously the spring still continues on towards the wall. You just want the point where the spring,
Until it compresses.
where the box stops. That's your 0 marker. So you know that this is exactly 30 degrees. So you could find that this height is equal to the sine theta times your hypotenuse, whatever spring that is. Does it tell you? No, it does not.
So I don't get.
Your hypotenuse is x.
Delta x.
Delta x.
Change in the x. Okay.
Yep.
Yeah, that's what I was thinking.
X.
So delta x sine theta.
So here, that's where it gets tricky, because you're going to have your sine theta delta x right there.
Okay.
So it's going to have like a quadratic formula kind of thing.
Wow.
So you have a squared here, and an x, and just a constant.
So we can basically say delta x, right? Just to understand it.
Yeah, do you want to say delta x?
No, just to say x.
X,
Because
okay.
we have x squared already, and if we put delta x, it's going to be confusing.
Okay, cool.
Okay,
So we'll just leave it at x. And now you have everything you need.
So then we use the quadratic equation to find the x, and that's going to give us two values, right?
Yeah. One of them is going to be negative, and you can throw that out.
Why?
Because it's never going to be negative.
Displacement.
Yeah.
Okay.
Like, you'll have things that go backward, that's a negative number, but like in the quadratic, it's going to give you something, on the other side, it's going to give you something really weird. And you'll just tell from what it is that it's
Okay,
weird.
so that's the first part. At what compression of the spring does the box have its maximum speed? What? Maximum speed.
At what compression does the box have its maximum speed? What does that mean?
So it's getting compressed, so that means the box should not have maximum speed.
Yeah.
Right, it's 44 meters.
At
Stopping.
what compression does this... I remember this one, and it's not... it's counterintuitive. It's very counterintuitive. Like, you would think that the fastest speed is right as it's about to hit, but it's not. It's really weird, though.
Do we know the mass of the object? Yeah, 10 kgs. So can't we do this? But then spring force.
I think it's saying at what compression distance. Like how
So,
far
like-
it compresses is the maximum speed.
Yeah.
So you would assume that the fastest is right here, right before it hits, right?
Okay.
But it's not.
Really?
Yeah.
When is it the fastest?
It's like right here.
How?
Because it's still accelerating down.
Okay.
And so it still has that acceleration. And so it'll still be gaining velocity up until that point. Then it starts to lose velocity. To get slower and slower.
Okay.
So like as you hit it, here's a graph. So like as you hit it with compression versus velocity. As the compression is 0, his velocity is like that. Then as the compression increases, it's like that, and then it decreases to 0. His velocity. So it's right there because he's still accelerating. Right here is like before he hits the thing, he's accelerating. So he's still accelerating here. Like the gravity doesn't go away, and so he keeps speeding up just really slowly. And then, as the compression force, the energy in the compression overcomes the acceleration, then he stops accelerating.
Oops. This is ugly.
Kinda, yeah.
Yeah.
So how would you do that? I say we graph it.
Graph it.
Can we?
Mathematical.
Sure, why not? Hey, check it out.
It's already opened.
Yes. I like it.
You have to use this.
Oh no. Okay. 1 divided by 2 times mass times v squared plus m times g times h. 1 divided by kx to the squared.
You're supposed to give values to those variables or no?
Yeah, let's say what's m is equal to, what's your mass equal to? 10.
You might want to declare global.
It's always good just to put that at the beginning of your every single assignment that you do.
Yep.
Mass is equal to, or I'd have mass g is equal to 9.81. What's K?
K is 250 newtons per meter.
What did we find for our velocity? Oh, that's right.
We did.
So your acceleration. So to find your velocity, that's v final is equal to v initial plus, it's gonna be squared, 2ax. Okay, that's good. Then what does that mean? V is equal to the square root of 2 times g times sine of theta. Is it g times sine of theta? Yeah, that's it. Times x, 4, just 4. Yeah, then I'm gonna plot that, see what happens. It's gonna give me an error.
Today's Friday.
Yeah,
I can't.
0 comma x comma 0 comma 10.
Somehow
I called it. Okay.
it always likes to play hard. Just as you're about to, you're about to enter the weekend, they always send you like these really impossible math homework assignments. I feel.
Hey. That's cool. I wonder what the x is, real quick. Well, that's what your x's are. So that's how far it displaces. It's 1.46.
Really?
Mm-hmm.
That's cool.
And then, how do you do it? So you can't graph it, because that just gives you weird stuff. So I wanted something like that. Wait, why did it not give me something cool? That's right, because it didn't.
Something cool.
Wait a second. What did it do?
Which question is this?
30. Did you do 30?
Yeah, I think I did.
How do you freaking find the mass if you don't? You just know that the carbon atom is 12 times the mass of the proton.
This one's a fun one. Yeah.
Carbon atom?
Yeah.
Like I set it up, I know what I need to do, but I don't know how to solve it without the mass of the proton.
Oh yeah, you don't know the mass of the proton.
If we knew the mass of the proton, we could find out the carbon atom because it's 12 times the mass of the proton.
Okay.
Ah, like that.
I wrote it symbolically.
Okay, so I got
can't
it.
solve it unless I know
Cool.
the proton.
Okay. So do you want me to answer yours? Then I'll answer yours.
Okay.
Sure.
Yes. No. Just because I'm excited because it actually worked now. Okay. So this is the graph, the thing, and we know that it's going to stop at like 1.5.
Okay.
So I'm just going to put 1.5. Okay. So see how it kind of still goes up,
Mm-hmm.
your velocity,
Mm-hmm.
as it still keeps going down.
Mm-hmm.
So that's what we're going to do. We're going to take that. Copy. Do the derivative of that. That, and set that equal to 0. Oops.
How come it turned all like dark and bold?
I have no idea. I don't like that.
Me neither.
That's your x.
So
Right
that's
there.
the compression.
Yeah, that's how far it goes, and that's the maximum velocity. So what that did, when you take the derivative, that finds the slope of the line.
Okay.
And you want to know where the slope is 0. It's like right there, because the slope right there at the top is 0.
Okay.
So if you find where the derivative is equal to 0,
There.
that is exactly where it's the x is. Yeah, that's where the velocity is a max. Yeah.
Sweet. Thanks.
And that's 1.96. Okay, so